stereocenter, and the final product will be this. Okay? Right? Okay. The next one, basically, they ask us how to synthesize this compound. This is up, then this is up. I put an ethyl, and I get this. Okay, then they say that we need to use the Evans auxiliary. Well, what we can see is that this is a one-free diol. That means if we are doing a fast group interconversion, we can get that this can come from this compound. Okay? Basically, I can, in order to come from here to here, I only have to do a reduction, which probably lithium aluminum hydride or something like this in order to generate the wedge. First, I can hydrolyze and then reduce. But basically, we saw this in when we put and we remove the Evans auxiliary. Okay, if this is coming from here, now this clearly is coming from an aldol, it's one hydroxyl free carbon group. That means that I can break this bond, and this is coming from this aldehyde plus this Evans. Okay, this is not anymore chiral. That means okay. Now I know from this is coming. Now I have to find which enantiomer of the Evans auxiliary I need to put. And how I do it? Basically, I put one. I put this up, and I test which will be the reaction if I put this up. Okay, remember that this has to be an aldol reaction. That means we have a charge transition state, remember? The lithium here, and then I always put the enolate in this position. Okay. Remember that one point when we are doing the enolate, we are turning butyllithium here, or terbutyllithium, or LDA, or whatever you want to use, is that the enolate that we form with the Evans auxiliary, remember, is always the cis one. Okay? Why? In order to avoid interaction with the substituent of the Evans. That means that I put here the ethyl, here the hydrogen, okay, the ethyl in the same direction as the oxygen, and here will be the chiral auxiliary that I will draw now. In this situation, I put the aldehyde with the R substituent in the equatorial position, and I am forming this one. Okay, this is one possibility. I draw now the chiral auxiliary, and remember, because we are in an enolate formation, in order to minimize the dipole moment, the carbonyl has to be opposite to the carbonyl of the enolate. That means that must be like this. if this is like this, the phenyl is going in front of us, isn't it? Yes. Right? If I draw the other 6-member ring, okay, I put the lithium here, and then I do exactly the same. I go here, the transition, the enolate with the ethyl down, okay, then I put here the nitrogen, okay, and then because I choose to put this kind of auxiliary up, this has to be going down. Okay, here I put the aldehyde with the R in equatorial position. Okay, we analyze these two. In this one, remember that I always put the enolate on the slide, and the benzaldehyde or the aldehyde is coming from in front of the slide. That means, in this case, this aldehyde and the phenyl are in the same phase. That means that this will crash with the phenyl. However, here the phenyl is going inside and the benzaldehyde is in front. That means that this will be the favorite approach. Right? I delete this, and then this that is the favorite approach. Basically what I do is to draw the final product. In this case, the final product will be, I started drawing right here, R, the OH will be inside, the ethyl will be inside, okay, and here I will have the enolate. I didn't do anything wrong. I will have this combo. Okay? I substitute the R for the substituent, that is the cyclopentane. This is the same anti-selectivity than this? Obviously not. I have the same diastereomer. If you have a different diastereomer, we are doing something wrong. We have the same diastereomer, however we have the opposite configuration. Here the OH and the ethyl is up, and here the OH and the ethyl is down. What I need to do, basically, I choose the bronc enantiomer of the chiral auxiliary. Okay, you don't need to draw it again, the only that you need to put is the opposite. That means that we will need to use this one, and that's all. Okay? Right? Okay. Next one is another aldol reaction, and what we are doing is we are using this aldehyde and we are adding this enolate. Okay, well, the only that we need to do, this is an aldol reaction, the only that we need to do is to draw the Bose 6-member ring. Again, I always put the lithium here, and then I draw the enolate on the slide, on the whiteboard, okay? Because this is like this, the isopropyl will be in this distance, okay? No, has to be the opposite. The isopropyl, because it's a trans must be this, and here is a hydrogen. Okay? And I will put here the carbonyl group with the substituent in the equatorial position. Okay? And what I do is to draw the chiral center. Okay, if I draw the chiral center, what I get, I draw the chiral center here, and I have to put the big substituent in this position, far away of the enolate, because the benzaldehyde, the aldehyde is coming from in front of the slide. If I do this, what I get is metal here and hydrogen here. Okay? The hydrogen is going inside, the metal down, and the phenyl is going to in front of the slide. I draw the other transition state. Okay? Exactly the same. I put here. Okay? This is the enolate, and then I put here and again I put here the aldehyde, this position in the equatorial, and then again I draw this with the phenyl here. In this case, if the phenyl is in this position, I have the hydrogen down and the metal inside. Okay? And then I analyze which will be more stable, which will be the best one, which will be the less energetic. Here I have the hydrogen that is going inside, crashing with the enolate. Here I have the metal that is going inside, crashing with the enolate. That means that this will be more favorable. Okay? I delete this, and then the only that I need to do is to draw this. If I draw this, here the isopropyl is coming up. Okay, and then the OH is coming down, coming inside. Okay, and this chiral center will not change. And this is the final configuration. Okay? How I did it, basically I draw the 6-member ring transition state, the Zimmermann-Krasner transition state, and then in this alpha chiral center I put the big substituent far away of the enolate. Remember that here we don't have to care about the syn-pentane interaction because we have a hydrogen in this position. Okay? Right? Okay. Then go for the next one. That basically is a Diels-Alder. What we have is that they told us that this compound is reacting with this. And the information that they give us, that this is quite important, is that the regiochemistry is in this way, in the way that is routed. That means that we will have this ring formation, okay? Why is what they tell us. In this case, should be very difficult to know the regiochemistry of this reaction. That means we will leave it, and what we need to do is to draw the transition state. Okay, the transition state is like this. and then the approach is of the double bond okay, this group can come from the bottom face or from the upper face. Okay, we don't know. We can analyze how it's going by the bottom face. If it's coming from the bottom face, remember that this is perpendicular to the slide. This terbutyl is facing down. That means that it doesn't crash with the die-in. However, if we put this that is coming from the top face, this terbutyl will crash with the die-in, making this approach, the top approach, unstable. That means that the approach will take place by the bottom face. If it's taken by the bottom face, then the only that we need to do is to draw the final product. Okay, I put the substituent that doesn't have any kind of center, that is this, and then this metal, if we are forming this bond, this metal is going inside. We are forming this bond from the bottom face, metal down, hydrogen up. Okay, here we don't care because we don't have any substituent, and then here, if this is forming the bond from the bottom, what we have is the ethyl going down and the hydrogen going up. Okay, and in the center, if we are forming from up, what we have is the carbonyl up and the terbutyl will not change. What we have is this final compound. Okay? And that's all. Right? Some of you can ask me why this, if this is the endo approach. Again, no idea if it's the endo or exo. This is a very complex structure. Normally endo and exo is very easy to determine when we have easy extraction with one substituent or two. This is very difficult, but whatever in the question they tell us that the addition takes place in this disposition. Okay? That means we use exactly what they say and we only analyze the approach. If it's the bottom approach or the top approach, in this case, must be the bottom approach. Okay? That's all. The other exercise about Biseau-Jesselyn, you can find it in the video of workshop 2. And I hope that this is useful. If you have any questions, send me an email and I will try to answer. Okay? Thank you very much for your attention and see you in the next lecture.